Welcome. Welcome to 2.5, rational functions. It'd be probably a good idea to define rational functions. You heard me mention rational functions from time to time in class. Let's talk about what they are. They are technically a quotient of two polynomial functions, and in the case of our definition, we're labeling them a of x and b of x. And b of x can't be 0. Why? Because that would make the denominator 0, so that's bad. With rational functions, there are potentially two types of asymptotes that come into play. One is a vertical asymptote, and the other is a horizontal asymptote. So we have a vertical asymptote at x equal to c. So vertical asymptotes should always be x equal some number. Why? Because x equal number, that if you were to graph x equal a constant or whatever, it would form a vertical line. Okay, so that's why it would be a vertical asymptote. And this happens to the graph if one of two things happens, as I wrote right down here. Limit as x approaches c, and this negative sign you may not have seen before. That means from the left. Okay, so remember how we talked about limits when they go from the left and from the right, they equal a number. So this is considering if the limit coming from the left is going to positive or negative infinity, or this positive sign up here means it's coming from the right. Means coming from the right is going to positive or negative infinity. And then horizontal asymptote over here, y equal to c. Why? Because y equal to c makes a horizontal line. It's a horizontal asymptote if, as we go to positive or negative infinity, it's going to be equal to some constant on the graph. Okay. Down below here, important to note, f of x equal to a of x over b of x. So here's how we write definition of polynomial. Okay, and we're going to need this in order to follow some of our asymptote rules. For our vertical asymptote, there may be, keyword may, because remember we talked about holes, right? So we may have a vertical asymptote if there's a value that makes b of x equal to 0. Okay. Now, with our horizontal asymptote rules, okay, we are focusing on, I'm going to use a different color for this, okay? Let's use red so it stands out. We are focusing on these terms right here, okay? Those are your leading coefficients of your numerator and denominator, okay? And what the horizontal asymptote rule says, if n is less than m, meaning the highest power on your denominator is bigger than your numerator, your horizontal asymptote is y equal to 0. If n is equal to m, then your horizontal asymptote is a sub n over b sub n. Okay, so if the highest power is the same, look at the coefficients, and it's going to be the numerator divided by the denominator. And then if n is greater than m, there is no horizontal asymptote, but it will be something we talk about later. So the directions for this one is determine any vertical horizontal asymptotes, graph the function, and state domain. Okay, so let's find the vertical and horizontal asymptotes here. So horizontal, what is it? Remember our rule. Highest power is in the denominator. So in this case, we know your HA is y equal to 0. Okay, and your VA, you find values that make your denominator 0. Can we factor out the denominator? You bet you can. What makes that 0? 1 and negative 2. Okay, so those are zeros. So when you go to graph this, where's your HA? Y equal to 0. VA, x equal to 1, x equal to negative 2. So we need to figure out what's happening between them. Okay. So as we do, what's the intercept first off? Do we have a x-intercept? Yes, we do, at 0, 0. Now, you might think, some people might have been told before that with the horizontal asymptote, it's never going to touch it. And I get what they're saying with that. But horizontal asymptote, this is why I talk about horizontal asymptotes in terms of limits. Because horizontal asymptote is what's happening as you go to positive infinity or negative infinity. And what you're going to see as you go to positive, negative infinity, it's going to just keep creeping up closer and closer. It's not necessarily it's never going to touch it at any point, but it's going to just keep getting closer and closer. What's happening in between? We're going to have a little bit of a line that goes like this. It's going to keep increasing as we get closer to that asymptote, and then it's going to keep going down that way, get closer to x01, going the other way. What's happening up here? If anything greater than 1, it's going to be a positive or a positive. So it's going to do one of these. And then negative, it's going to end up getting us negative over positive over here. So it's going to do one of these. You pick a couple points, the key is simple, and you'll see that ends up looking like that. Now we're going to talk about the scenario when the numerator has the highest power. Okay, and those are called oblique asymptotes. Okay, so if we talked about dividing polynomials before, right? Yeah. So when we have the numerator divided by the denominator, we got a quotient. So if your highest power is on the numerator and you divide whatever your quotient is, that is going to be your oblique asymptote right there. I made my squiggle a little too long. But point being, if whatever this is, I've asked for the oblique asymptote, it's that. Okay, when you divide, whatever your quotient is going to be your oblique asymptote, and then what's left over is how the graph will look from there. Let's do an example together. In this example, I'm just finding the asymptotes and intercepts. So I got to divide the highest powers in the numerator. What times x will get us x squared will be x. So x squared is 4x. Subtract, you get negative x minus 3 minus 1, negative x minus 4. Subtract, you get 1 left over. So what does that mean? Your solution is x plus 4 plus 1 over x minus 1. Excuse me, x plus 4, because we're divided by. Oh, I mixed it up badly. Oh my. Because our solution was x minus 1. So we're going to have a slant asymptote of x minus 1 is what that's saying. Or an oblique asymptote. Like, the names are interchangeable. You can call them oblique or slant. Okay? Now, we will still have a vertical asymptote at values that make the denominator 0. Okay? So we'll still have a V8 of x equal to negative 4. So that's 1. We have an oblique asymptote at x minus 1, y equals x minus 1. And then we have intercepts of the values that make the numerator 0. Go ahead and use quadratic formula, but I'm going to tell you right now, you're not going to find any. So, I have this. No x-intercepts. Do we have a y-intercept? Yeah, you betcha. We have a y-intercept. When x is 0, what do you get? You'll get negative 3 over 4. How do I get that so fast, you might ask? If this goes to 0 right here, and then this goes to 0, I'm left with negative 3 up top, and then this goes to 0, I'm left with 4 on the bottom, then you get negative 3 over 4. Wow, what is that? So, I answered the questions. I'll show you how the graph might look something like this in class. I mentioned holes earlier in the year. So, what are holes? So if I have the numerator and denominator, right, and we have a value that makes both the numerator and denominator 0, that value is the hole. Okay, I have the formal definition right here. Write it down. So in this case, the hole would be at x equal to a. Okay, x equal to a would be the hole. That value would make both numerator and denominator 0, whatever that value of a is. Let's run an example. So we have two polynomials in numerator and denominator. Always factor. We want to know what the zeros are. So let's find out x plus 6, x plus 4. And we have x plus 4 and x minus 3. Are any of these factors the same? Yes. X plus 4. So therefore, x equal to negative 4 is not the vertical asymptote, and it's not an intercept. Okay, it's a hole. Now, what we can do to find out specifically where that hole is going to be, when we cross out the x plus 4's and we put negative 4 into the function, we're going to get 2 over negative 7. So the hole is exactly at negative 4 comma negative 2 over 7. Also, if I were to ask you for everything else, BA is x equal to 3. HA, your powers are the same, so the coefficients is 1 over 1. So HA is y is equal to 1. Intercepts, x-intercept is values make the numerator 0, so we have an x-intercept at negative 6 comma 0, and we have a y-intercept. We put 0 in for x, and you're going to get 0 comma negative 2. Once again, set everything over here equal to 0, and then you're left with 24 over negative 12, which becomes negative 2. All right, last part of this video, solving rational equations. So first, we always want to factor. So in this case, in the left problem, we don't have to factor because nothing is factorable. Then after that, we multiply by everything that's in the denominator, x minus 2. Why? Because it's going to eliminate that denominator, leave me with 9x equals negative 6 times quantity x minus 2. Distribute. And then let's isolate. 15x is equal to 12, divide by 15, and you're going to get an answer of x is equal to 12 over 15. That reduces to what? 4 over 5. Now for the second one, we will have to factor a little bit. So 2x over x plus 3 plus 3 over x minus 6 equals 27. You factor that. Factors of negative 18 up to negative 3. Negative 6, positive 3. I'm using different color to kind of help us decipher between the left problem and the right problem a little better. And so what do I see? I see I want to multiply everything by x plus 3. So when I do that, x plus 3 goes away there. X plus 3 goes away there. There's no x plus 3 in this rational part of the function. So I need to put that on the numerator. It's going to give me 2x plus, if I distribute the 3 to both terms, I'm going to get 3x plus 9 over x minus 6 equals 27 over x minus 6. Now, what do we have on the denominator now? X minus 6. Let's multiply everything by x minus 6. That goes away by, and then distribute 2x both terms, going to get 2x squared minus 12x plus 3x plus 9 equals 27. Like terms, subtract 27, you get negative 18. See, does AC method work for this? Yes, AC method does work for this, because 2 times negative 18 is negative 36. Factors of negative 36 out to negative 9 is negative 12 and 3. So 2x squared plus 3x minus 12x minus 18 equals 0. Group. You're going to get x parentheses 2x plus 3. And then GCF and negative 12x and negative 18 is negative 6. We get a common one? Yes, we do. So we're going to be left with x minus 6 and 2x plus 3 equals 0. Two solutions on both equal 0. Your two solutions will be 6 and negative 3 over 2. Now, these problems, you should always check them, okay? And one should stick out as a red flag immediately. That is x equals 6. Bye. How do I know that so quickly it's not going to work? If you put 6 into the original function up here, that's going to make the denominator 0 of one of them. You can't do that. You know that. So therefore, we know x equal to 6 will not work, but negative 3 over 2, go and plug it in. It will work on both sides of the equation. I appreciate you. I appreciate you watching, and have a nice day.